Okay. So, let us come back to the same equation that we have derived in the previous class, that is the x t, which is in the FM demodulator circuit. That is where we are now. So, now we want to see the effect of this thing. Okay. So, after the band pass filter, we have already characterized the signal plus noise. So, this is the noise part. To characterize this, let us try to draw a phasor diagram, which is very famous in FM. So, what we will do, we will try to draw the phasor diagram. Means phasor means already we will be actually putting the phase in angle, and the amplitude will be put over there along the radius of that. So, it will be a 2-dimensional diagram. Now, in any phasor, the reference is very important. So, here what we will do, we will take the reference as this one, signal reference. So, that must be the reference where we should start. Okay. So, this is something we call as let me see, that is called as phi t. Okay. So, we are calling this particular part as phi t. Okay. So, we can even write this as AC cos 2 pi f c t plus phi t. So, we are just writing that as a phase phi t, then r t cos again 2 pi f c t plus some psi t. Okay. So, this is the reference. So, therefore, I can put AC over here, because in phasor it is whatever the angle. Now, this angle is taken as reference. So, that must be the 0 angle. With respect to that, we will have to put this. Okay. What is the angle of that one? Okay. And these are in phasor, this will be 2 vectors, right, which has this angle and this angle. Okay. So, this is the reference angle. Therefore, what is the angle of this one, of this phasor? That must be this minus this, right, that is the angle. So, that must be 2 pi f c t gets cancelled. So, psi t minus phi t, that becomes the angle of this one, okay, with respect to this reference. So, remember that we have taken the reference with respect to this. So, that becomes the 0. So, therefore, this angle, this entire angle, because phasor is just something cos something. So, therefore, that amplitude gets into the radius of that particular part, and the angle will be, corresponding angle will be this one. So, it is just a polar plot where the amplitude is the r of that polar coordinate, and theta is the theta it has. Okay. So, with this reference, so we have this amplitude as AC, and we get this one drawn. So, this will be having amplitude RT, whatever that is, and this will have a phase of psi t minus phi t. Now, that should look like something like this, okay, because we are adding these two. So, in vectorial we can write from here that one same phasor. So, this angle should be this angle. So, therefore, this must be psi t minus phi t, right. So, overall this x t must be the resultant one, resultant phasor. So, that must be my x t. Okay. So, this is just a phasor representation of that whole thing. Okay. So, immediately that must have some angle. Okay. Let us call that as theta t. Of course, it is reference to this one. So, this must be theta t minus my phi t, right, because the reference is already phi t. So, therefore, if this has some angle theta t, therefore, the actual angle between these two should be theta t minus phi t, right. So, now I can write this theta t minus phi t. How do I represent that? So, basically I can see from the phasor diagram that tan of this must be this divided by this. Okay. So, if I put a perpendicular from this point to this point, this entire thing divided by this entire thing. So, just this angle should be tan inverse of, or maybe you can write it fresh. So, this angle should be theta t minus phi t should be tan inverse of let us see the diagram. So, that should be this divided by this. What is this? This should be RT sine of that, sine of this angle, and what is this? This should be AC plus RT cos of this angle, this internal angle. So, I can write it as RT sine of the internal angle is actually according to me psi t minus phi t divided by AC plus RT sine of psi t minus phi t. Sorry, this should be cos. Okay. So, that is all fine. Now, whenever we are doing analysis of noise, we expect that noise has to be that is lesser power compared to my actual signal or that AC. So, basically my RT should be always much lesser than AC, that approximation we can always take. So, immediately I can neglect this part. So, I can write this, that theta t is equal to, I can take this phi t on this side, plus I can have this tan inverse of this divided by AC. Again it is RT by AC. So, I can again neglect because that angle will be smaller, because sine can only get up to +1. So, the maximum value will be RT by AC. So, which is again RT is smaller than AC. So, tan inverse of theta must be equal to theta. So, I can write this as RT approximately RT sine psi t minus phi t divided by AC. Okay. So, this is, there is an approximation which is valid as long as this condition is true. Okay. So, I get my overall theta t, which is actually the phase of the resultant signal, that means that x t. If you see over here, that is the phase of x t. What discriminator will do or what the FM demodulator will do? It will actually take that phase, differentiate it, whatever that is, that must be my signal. Okay. So, discriminator output should give me the differentiation of this phase, right. So, basically my output signal, let us call that as let us say Vt, because if we take this diagram, so that is the Vt. So, the output should be Vt should be, according to my understanding of discriminator circuit, that should be differentiation of this phase. But remember, the differentiation of the phase gives you the omega variance. So, if I need to have frequency variance, which we are doing for this calculation, so there must be 1 by 2 pi. So, 1 by 2 pi d d theta, sorry, d dt of this theta t, that must be what we expect after the FM demodulation. So, let us try to see that. So, it should be 1 by 2 pi d phi t dt, okay, plus there should be d dt of this one. Okay. Let us first try to, of course 1 by 2 pi should be there. Let us try to evaluate this part. What was my phi t? So, phi t was 2 pi k f integration minus infinity to plus t m alpha d alpha. So, what is d phi t by dt? Integration and differentiation gets cancelled out. So, it should be 2 pi k f, and if I differentiate it, that should be empty, right. So, I must expect this. So, therefore, V t if I write, so 1 by 2 pi into d phi t dt, that is this one. So, that should be 2 pi k f m t, 2 pi gets cancelled, plus I have 1 by 2 pi d dt of this whole thing R t dot 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 divided by AC, right, whatever we have derived. This is exactly my message signal, that is very good. So, this must be accounted as noise overall, but the problem is if I just try to put that as, suppose this is as NDT. So, what do I get as noise NDT? That must be 1 by 2 pi ddt of RT sin psi t minus phi t AC. Right. What I can see is there is a psi t and phi t. Psi t is completely related to the noise, I have no problem, no issue with that, but phi t is still related to the message signal. So, in that noise there is a part of message signal already. Okay. So, that is where we have to be little bit worried that this noise has some message signal part. Now, again we will talk about something which will not prove because of time constraint. So, that was means that derivation came from a famous paper written by Rice at 1963. If you are interested, go to that paper, it is a very famous paper for FM noise analysis. So, what he could prove is that this particular noise is independent of the message signal. Okay. So, whatever the message signal is, it is independent of that, and not only that, he could also prove that, see, this psi t already we have shown that it is actually, without proof we have said that it is actually it is a random process which is having uniform distribution between 0 to 2 pi, right. So, what he could prove that this also, which is independent of message signal, even though phi t is there, it will be independent, it will become independent, and this is also uniformly distributed between 0 to 2 pi. So, basically what I can do, instead of taking that part, we can just take this as sin phi t. So, this was the approximation he could take, and he could prove also that this approximation is valid. So, therefore, I can write this without loss of any generality. AC is a constant, so that goes out. So, d dt of RT sin psi t. Can you identify this? What is this? This is actually the quadrature term. Go back to my filter representation of a band pass signal, you will see that RT sin psi t is actually the quadrature term of the noise. Okay. So, that is NQT. So, therefore, immediately we can say the FM noise, which is NDT, is nothing but 1 by 2 pi AC, and then it is ddt of this RT, or I can say NQT. Okay. So, this is something we can already say. Okay. So, it is 2 pi 1 by 2 pi AC differentiation of NQT. Now, NQT we already know, right. So, NQT is something like this. If eta 0 by 2 is the noise strength, so it should be eta 0, because it has to be shifted left and right, they will superimpose, we have already done that. So, it will be N 0 over the desired band. So, that band becomes Bt divided by 2 up to Bt by 2. Okay, fine. So, this is the overall NQT. Now, let us try to see what this means, NDT. So, NDT is nothing but this NQT passed through a ideal differentiator, because that is the operator which is being operated over NQT. So, it is nothing but a circuit which is an ideal differentiator, and you pass your NQT, whatever you get at the output, that is NDT with this factor. Okay. That factor is all right, we do not have to bother about that factor. Okay. So, that is what is my NDT, right. So, let us now try to see ideal differentiator. What is the Fourier transform of that? That is actually j 2 pi f. So, this is the Fourier transform of that. We have already proven that ideal differentiator also a linear time invariant circuit, that we know already. Okay. So, if we have a random process, input to a, this is something we have proven, input to a linear time invariant circuit, then the output random process will be mod HF square, where HF is the transfer function of that particular linear time invariant circuit or whatever you put, into the input SIN or power spectral density. So, basically we can write power spectral density of this NDF must be equal to the mod HF square, which is 2 pi f whole square, into the this part SNQF, and you also have this part. So, therefore, it should be 1 by 2 pi AC whole square. So, this must be my SNDF, so that characterizes my noise after the discriminator circuit. Okay. So, what do I get from there? So, I get this SNQF is already there, here 2 pi square gets cancelled. So, I get F by AC whole square SNQF, right. So, this is what I will be getting, and this is defined. Remember, the filtering was already employed. So, this must be defined from minus Bt by 2 to plus Bt by 2. So, this is true if my mod F is less than equal to Bt by 2, and this must be 0 because otherwise there is no noise, because it has already been cancelled due to the ideal nature of band pass filter. So, that must be 0 otherwise. So, can I now plot this? Okay, so, if I plot this, SNQF is something like this, which is constant between minus Bt by 2 to plus Bt by 2, but SNDF that has f square. So, at 0, frequency 0, it must be 0, and then it should have a parabolic thing. So, it must be something like this. Okay. So, this is the FM after demodulation FM noise characteristics. So, it never remains similar as AM, any other AM counterpart, because in AM counterpart always whenever we were analyzing the noise, it was like this, but this is what is happening. If you think little bit carefully, we have already proven that interference effect. If you take all this noise as if small at a particular small band, small amplitude of interferers, what FM does? It captures it, right, and closer to the FM it captures it more, that means it suppresses it. Same performance is happening over here. As you can see, closer to the central frequency, it is actually suppressing those noise, and as you go away from the central frequency, it gets some significant part. Okay. So, FM due to the capture effect only, here the physical meaning is again that same capture effect we have talked about, but you can see now mathematically that that is what is happening. So, FM due to capture effect actually shows this particular thing, okay, this kind of representation. Let us now try to see what will be the overall noise. Okay. So, now this is my noise, and at the output we are also getting the signal part was this part Kf into Mt. Okay. So, this is the signal, and the noise whatever NDT we have talked about, that is the power spectral density of this. Now, these two things we will be putting. Now, already my signal has come into the baseband. After the modulation it is just empty. Now, the signal is defined from minus W to plus W. I have noise which is defined due to that band pass filtering, and after that whatever demodulation has happened, my noise is still defined from minus Bt to plus Bt. Now, this is FM bandwidth. FM bandwidth we have already proven through Carson's formula that it is, be it narrow band or wide band, whatever it is, Bt is always bigger than W, okay, or that Bt by 2, which is one sided FM bandwidth, that is always bigger than that W, which is the message bandwidth. So, for sure I know this Bt by 2 is greater than equal to W. So, I can now employ, because my message will be somewhere here only within W. Beyond that, whatever is there, that is not required for my signal, and I can also see due to FM capture effect, that is where the noise is having higher power. So, I should employ a low pass filter around that message signal, okay, going from minus W to plus W. So, that is what I will be doing next. I will be passing it through a low pass filter of bandwidth W. So, it will actually take from minus W to plus W. So, this will definitely have lesser noise. So, if I now integrate this power spectral density, whatever I get, that must be the noise power. So, let us try to calculate the noise power. So, I can now define, after doing this low pass filtering, this SNDF must be same thing, F by AC whole square SNQF, where mod F now less than equal to W, because it is restricted to that, because I have already done a low pass filtering and it will be 0 otherwise. So, what is SNQF in that? So, that is just N0. So, I can, instead of this, I can write N0, right. So, what is the overall power? Overall power we know from power spectral density, you have to just integrate it. So, here it is defined only from minus W to plus W. So, the overall power of noise should be integrated from minus W to plus W, this F square SE square N0 dF, right. That must be my overall noise power. So, N0 by SE square goes out, this is F square. So, it will be F cube divided by 3, and then if you put W, so that becomes actually 2 W cube divided by 3. This is the noise power. Okay. What is the corresponding signal power? So, I had Kf into MT. Okay. If the signal power, overall signal power is P, so this should be Kf square into P, that must be my signal power. Therefore, what is the signal to noise ratio for FM? So, the SNR for, let us say, FM is equal to, signal power is Kf square divided by P, and noise power is, if I just put it, 2 W cube 3 SE square, right. This is what we get as SNR of FM. Now, we have to do the figure of merit calculation, right. For figure of merit calculation, what we have to do, in the baseband we have to transmit whatever we have transmitted for, whatever power we have put for FM transmission. FM was just AC, something is there, okay. So, what will be the power of that? That will be AC square by 2, because whatever inside, that is just phase, that will not contribute to the power of this signal. So, AC square by 2 will be the power that will be transmitted in the baseband. And what will be the noise? Noise goes from it will have a strength of eta 0 by 2, and it goes from minus W to plus W. So, overall noise will be N0 into W if we integrate. Okay. So, that is the noise power. So, therefore, overall SNR for the reference one should be this AC square divided by 2 N0 W. So, therefore, the figure of merit, that must be this divided by this, right. So, figure of merit must be 3 SE square Kf square into P divided by 2 N0 W cube divided by this. So, this particular term goes up, 2 N0 W divided by, that is the multiplication part, AC square. So, AC square gets cancelled, N0 gets cancelled, 1 W gets cancelled, 2 gets cancelled. So, we are left with 3 Kf square P divided by W square. Okay. That is the figure of merit. probably from here we are not able to appreciate what has happened, okay, in FM. So, that is something we still do not know. Let us try to evaluate it in terms of a tone modulation, then probably we will be able to match it with respect to AM, what happens. Okay. So, let us try to do a tone modulation. So, in tone modulation what will happen? My MT, that is actually nothing but some cos omega MT. Okay. This is just a tone modulation, this is just a cosinusoidal I am trying to transmit. So, immediately I can calculate what is the power of that. So, that means P should be half because it is just a cos. So, P should be half, this is something I know. Okay. What will be my ST? ST should be AC cos of 2 pi FCT plus I will have KF, and then if this KF is represented in terms of let us say omega. So, then that is KF, otherwise there should be a 2 pi, all those things. Okay. So, if that is the case, so KF, and then I need to have a integration of this one, integration this. So, if I just do a integration, what will happen? If I do integration, that should be sin omega mt inside divided by omega m. Now, if Kf is represented in frequency, so that must have 2 pi. So, I can here also write 2 pi Fm, 2 pi gets cancelled. So, this is my representation. Okay. So, I can write this as AC cos 2 pi Fct plus Kf by Fm sin 2 pi Fmt. Okay. So, that is my representation. Now, the figure of merit which we wanted to calculate, what is that? That is actually 3 Kf square P divided by W. Okay. What is the W for me? That is actually Fm, because the message signal is having just an impulse of strength 1 by 4 at plus Fm and minus Fm. So, what is the overall bandwidth? That should be this only. So, W becomes my Fm, right. P becomes half. So, I can write this as 3 by 2. Okay. So, that was W square of course in the formula. So, P becomes half, then I have Kf square divided by Fm square, or I can write 3 by 2 Kf by Fm whole square. Can you now identify what this is? This is actually the beta. We have already proven that for tone modulation, that Kf by Fm is the beta, or the, we should say, modulation index or frequency deviation index. Okay. So, this must be the beta. So, I can write this as 3 by 2 beta square. What now I see, that now we get a particular relationship between the FOM, figure of merit, with respect to beta. The good part is, here if I increase beta, my FOM increases. That is one thing. What does that mean? That means if I increase beta, I am actually going towards a wider band FM, because the frequency deviation, that means the Kf value is getting increased with respect to Fm. That means the frequency deviation is getting increased, which is actually termed as wider band FM. So, if I make the FM more wider, that means I increase the bandwidth of FM, I get a benefit in terms of noise cancellation, because its figure of merit gets improved. So, this is what we wanted to discuss, that FM is the only modulation scheme, none other modulation scheme will probably do that, where I can exchange my frequency with respect to noise and means noise performance. So, if I exchange means I can make this worse and get a better benefit. So, basically I can increase the FM bandwidth where I am guaranteed to have a better performance in terms of noise cancellation. This is what is happening in FM. Now, let us try to compare this. What was the best FOM, figure of merit, that we could get for AM? That was 1/3 we have proven with a tone modulation. So, what we can write that this, if this has to be anything better than this 1/3, my 3/2 beta square must be greater than 1/3. Okay. And then immediately I can get a beta which must be greater than √2 divided by 3, which comes out to be some 0.471. So, any beta which is greater than this will always give me benefit in terms of noise cancellation with respect to FM. So, that will be happening, and I can take to any beta value where this will be much bigger. Okay, I can. So, basically I have now a controllability parameter or a controllable parameter which I can just keep controlling to get better and better noise performance. So, in FM you can actually do, you can make the bandwidth wider, of course the bandwidth spectral efficiency will be reduced, but you get better signal quality. That is always possible, whereas in FM you can never do that. If you increase bandwidth, more noise will be coming inside and you will get a worse performance, and you cannot decrease the bandwidth, because the bandwidth that you take for AM, that is the optimal one. Anything you decrease, your signal will be distorted. So, there is no option over there, no variability over there, whereas in FM you can do that. And this is also the reason why people have preferred wider band FM compared to narrow band counterpart, because in wider band FM you can get a better noise cancellation, and that is why we have seen that Armstrong tried so hard to generate wider band FM with series of multiplier circuit from a narrow band counterpart, because generation of narrow band was that time easy when VCO was not there, and then they could actually reproduce wider band FM by doing this. Okay. This also gives us another advantage. If you just try to see what was the FM noise performance, this was the noise spectrum, whereas the message will be, so this is from -W to +W, whereas the message will look like this. Okay, so, from -W to +W, or it might have nothing around 0, that is what, if it is a voice signal. Whatever it is, we can see that the more noise are added at the higher frequency part. So, to combat that, what we can do some pre-processing at the signal level. We can give something where the signal higher frequency components are boosted compared to the lower frequency component, because lower frequency component are much better off in terms of noise, because they are getting added with lesser amount of noise, whereas the higher frequency component are getting more amount of noise. So, if we just boost them little bit, what will happen? We will get a better signal to noise characteristics at the higher frequency, and then after doing FM demodulation and everything, we can actually, whatever boosting we have done, we can just reverse that. So, that means after noise cancellation and everything that has been employed, we can just redo the whole thing and we will get probably a better analysis, because noise power will be already same whatever will be coming in, and after that if we do a reverse whatever filter we apply at the beginning, if we just reverse it, we will probably get a better performance in FM. So, that is what people have employed, which is famously termed as pre-emphasis and de-emphasis. So, you do a pre-processing of FM signal to give it a better noise cancellation. So, next class probably we will be discussing this pre-emphasis and how much it gives benefit with a practical circuit. Okay. Thank you.